Section 5.8, Complex Eigenvalues. We will pick up in this section where we left off in 5.7, solving systems of first-order linear homogeneous differential equations. But, as the title of this section suggests, the problems that we encounter here will involve matrices which have complex eigenvalues. This is an issue that we confronted in Chapter 3, and in Chapter 3 we utilized Euler's formula to rewrite complex exponential functions in terms of sines and cosines, did some manipulation, and were able to generate real-valued solutions to our differential equations that were built out of exponential and trig functions. In this section, we're going to borrow that methodology, and in fact, I'm going to kind of skip through some of the steps, but intuitively, I anticipate that the solutions that we encounter in this section will once again involve not only exponential functions, but also trig functions, sine and cosine. One important thing that I want to point out before we start looking at some examples is a key property of eigenvalues and eigenvectors of real-valued matrices. So if I have a square matrix and all of the entries are real numbers, if my eigenvalues are complex, we know that those eigenvalues come in a complex conjugate pair. This is a result that we saw in Chapter 3 when dealing with the characteristic polynomials of that chapter, and it's essentially a function of the structure of the quadratic formula. If I have a quadratic characteristic polynomial, then the only way I will encounter complex roots is if the discriminant, the value underneath the square root in the quadratic formula, is negative. Here, let me write out that quadratic formula so I can be a little bit more explicit. So as we know in the quadratic formula, the only possibility, if a, b, and c are all real values, the only possibility for complex values to come out of this equation is if this discriminant, sometimes called delta, is negative. Well, if this quantity is negative, then the structure of my roots, or my eigenvalues, will be some real number plus or minus a number with an I in it. So that's why we know that eigenvalues will always come in a complex conjugate pair. What's less obvious is that eigenvectors will also come in complex conjugate pair. So whereas I know that my eigenvalues will have a form that we could write like this. Actually, that's a typo because I'm missing the I here. So I would have an I. So lambda plus or minus mu I. For some real numbers, lambda and mu. And then in addition, we know that the corresponding eigenvectors will have that same complex conjugate structure. They can be broken down as some vector plus or minus I times some other vector. Now, before we actually talk about how to use these ingredients to build this solution of a differential equation, let me do one quick example where I just calculate eigenvalues and eigenvectors to demonstrate the property that I was just discussing. Let's take a look at example 1. Here I just have a square matrix, a 2 by 2 matrix. This is not part of a differential equation, but I just want to find the eigenvalues and eigenvectors to explore the behavior that we just discussed. So here I've started those steps to calculate my eigenvalues. One important thing to point out, my original notes had a typo. So I've corrected it here in sort of red ink. The notes that are posted in BB Learn should be correct. So hopefully you have the correct matrix, but that entry needs to be a -2. Otherwise, I don't get complex eigenvalues, and that wouldn't be very helpful in this particular context. So using this matrix, I get complex eigenvalues of 1 plus or minus 2i, and of course I expect that if my eigenvalues are complex, they will have this complex conjugate structure where it's a real number plus an imaginary number and then a real number minus the same imaginary number. And that is, as I pointed out a second ago, mostly due to the nature of the quadratic formula. Next, I will proceed as usual. I'll choose one of these eigenvalues. I'll go ahead and choose 1 plus 2i and plug it into the eigenequation as appropriate and try to find the corresponding eigenvector. All right, so I have taken lambda equals 1 plus 2i, plug that into this form of the eigenequation, and work through the steps to find the corresponding eigenvector eta. I'll color code that eigenvalue eigenvector pair as I like to do. And there's just a couple details that I want to point out here. First is this system is a little strange, and anytime I run into a system where I have complex values, I expect the algebra will look a little weird. So for example, I believe I've plugged this in correctly. I've plugged this in correctly, and now from this form of the matrix to this step here, I have assumed that this second row will be canceled out. The way to actually do that in matrix form is a little bit complicated because I have to try to get this coefficient to cancel this coefficient. And so in the name of efficiency, shall we say, I have just assumed that that's going to work. And so I've just taken the top row of this system and figured out what eta needs to be based on that. If you want, you can double check. It's not too hard if you write out this second equation and then make this substitution for eta 2. You will see that this second equation simply yields 0 equals 0. But I did just want to point that out in case it wasn't clear how I got from this step to this step. The other detail that I want to mention is that this is my eta vector here, based on my calculations, and there's no reason I can't write it in this way. But what I've chosen to do in this additional step is to separate the real part, the part that doesn't have any i's in it, and the imaginary part. Moreover, I've actually factored out the I. Again, if it's not totally clear how I got from this vector to this vector, maybe imagine multiplying or combining these two vectors. So you would multiply this I in here, and then we would add these two vectors component-wise, and you see that I do get this eta that I started with. This may seem like an unnecessary step or unhelpful step, but this structure where I have separated the real part of the eigenvector and the imaginary part of the eigenvector is kind of the point that I'm trying to demonstrate in this example. So I wanted to make sure to write it in that specific way. All right, our other eigenvalue is lambda equals 1 minus 2i. So let's go ahead and do the calculations necessary to find the corresponding eigenvector. Now the key detail that I want to point out is we know that my eigenvalues are a complex conjugate pair. Some real number plus something, same real number minus the same thing. If we look at our eigenvectors, and again, I mentioned a second ago that this was kind of an awkward way of writing this eigenvector, but if I choose to write it in that way, then you'll notice that the corresponding eigenvectors are also complex conjugate pair. In each one, I have 1, 1, and 0, negative 1 times I. Up here in this eigenvector, they're added. In this eigenvector, they are subtracted. So again, I admit that this representation may not be totally obvious or the most efficient way to write this vector, but it demonstrates this conjugate structure between these two eigenvectors. The reason I'm taking all this time to point this out is because this means if I ever find that my matrix has complex eigenvalues, I don't need to work through all of the steps to find both eigenvectors. Once I have found one eigenvector, I know that the other eigenvector will be the conjugate of that one. Also, I'll just point out that I have intentionally written these in such a way that this sign agrees between the eigenvector and the eigenvalue that it was derived from. And that's true for this pair as well. Here there's a negative between the two, therefore there's a negative between these two vectors. As we'll see in just a moment, these two separate vectors are going to be key ingredients in building the general solution to a system of differential equations that has this type of coefficient matrix. So let's take a look at the theorem that tells us how to build that general solution. In this first paragraph, I just remind you again to take a look back at section 3.3 to see how we used complex exponential functions to build real-valued solutions, a real-valued general solution. Similar techniques are used in this case, but I haven't worked or shown all of the details here. What I've done instead in Theorem 1 is I've gone directly to the form of the general solution. So Theorem 1 says if A is a 2 by 2 matrix whose eigenvalues are, there's that same typo again, I must have copied and pasted. We need an I in there, lambda plus or minus mu I, and the corresponding eigenvectors will have the form what I've called A plus or minus bi, or ib. So again, I'm utilizing that conjugate structure of the eigenvectors. Then, in order to be able to build the general solution of the system, where this matrix A is the coefficient matrix in the first order linear homogeneous system, then I put those ingredients together in this way here. Now, I recognize that this solution looks pretty complicated, but let's just break it down and look for some familiar ingredients, try to understand exactly how we're using these 4 ingredients essentially to build this general solution. First of all, e to the lambda t is exactly the exponential that we would expect given that our eigenvalues have this form here. Similarly, this mu in the imaginary part of my eigenvalues, I'm not surprised to see that inside the sine and cosine along with t. Both of those features are features that we've borrowed directly from the chapter 3 methodology. So then how about these vectors a and b? It's not totally obvious how we've put them together to generate this general solution, but as I said, you can either look back at 3.3 or look in our text where the author briefly describes how you can build these 2 solutions. But basically those coefficient vectors, those vectors, those components of my eigenvectors are acting as coefficient vectors on the cosine and sine terms, respectively. The one key detail here is that it is customary to subtract these 2 terms in this first component and then add those 2 terms in this second component. So I hope that this form or this structure isn't too daunting, and we'll see in a second how once we've got all the necessary ingredients, it's just a matter of identifying exactly what role they play in this formula and putting everything together. So let's go ahead and give that a shot. In example 2, we want to just use the system whose eigenvectors and eigenvalues we solved for in example 1 and find the solution to the system of differential equations where that matrix is the coefficient matrix. Let me jot down the eigenvalues and eigenvectors from example 1 for reference. And now, just since this is our first example and we're just getting accustomed to these different components, let me label all of the ingredients that are provided in Theorem 1. This notation is a little unfortunate. I'm calling just the real part of my eigenvalues, I'm calling that lambda, and then I'm calling the imaginary part mu, and then this first vector will be my vector A, this second vector will be my vector B. Once I've identified all those ingredients, it's just a matter of following this recipe here in a certain sense. So let me write out my general solution. I can see that the broad structure of this solution is that I have a constant times an exponential, another constant times that same exponential, and now here in parentheses, I have these sine and cosine expressions. Let me go ahead and write those out. So plugging all those ingredients in, this is what I get as my general solution. As I've mentioned previously, this is an acceptable form of that solution, but sometimes it's helpful to divide this up into the sort of first solution as determined by the first row of this vector or matrix expression, and then the second solution, x2. Let me go ahead and give that a shot and write out these 2 solutions. And in this particular case, there's even kind of the possibility of doing further simplification. For example, in x sub 1, I could factor out e to the t cos of 2t, and then I simply have the constant c1 plus c2 inside the parentheses. Or looking at x2, I could probably use a trig identity of some sort to combine these, or maybe I want to again factor things out. I'm not interested in taking those steps at this point, but I do like to write this out just to kind of verify that these are in fact the types of solutions that I would expect. Based on our experience in chapter 3, when we have complex solutions to the characteristic polynomial, I expect to see trig functions that are driven by exponentials in some respect. And that's exactly what both of these functions, both of these solutions turn out to be. Let's go ahead and take a look at the next example. In example 3 here, we're given an initial value problem where we've got a system and an initial condition or initial conditions, and asked to solve that. As always, we'll start by finding the eigenvectors and eigenvalues, the eigenvalues first, I guess, of this coefficient matrix A here. So let me work through those steps. So here's what I get when I work through the details using the eigenvalue -2 plus I. Once again, plugging that into my eigenequation is kind of weird, but one step of simplification, and then I'm going to assume that these will cancel, one row will cancel the other out. And then in this particular case, I've chosen to take this second row as in order to use that to define what the vector eta needs to be. So this, remember, these are coefficients on these individual components. So this says that -1 times eta1 plus 1 minus I times eta2 has to equal 0. I can, of course, move this eta1 over to the right-hand side. Now this equation here defines the relationship between eta1 and eta2, the two components of my eigenvector. And then just to point this out, if you were to take this and plug this in to the first equation and simplify, you would see that that first equation would yield 0 equals 0. So if this relationship must be true, again, the way I read this is this tells me I can pick anything I want for eta2. And so I have chosen to pick eta2 to be 1, and then eta1, the first component, will be 1 minus I times my choice for eta2. And since I chose eta2 to be 1, my first component here will simply be 1 minus I. As we saw in example 1, there's nothing wrong with this form of the vector, but I do want to push it a step further and break it into this form here so that I can clearly identify the A vector and the B vector that will be used for my general solution. And now this seems like a lot of work, but remember, in this particular context, there is the advantage that I don't have to work through the steps necessary to identify the second eigenvector. We know that just as the eigenvalues come in conjugate pairs, so too the eigenvectors will come in conjugate pairs. So I know straight away without doing any calculations that this will be my second eigenvector. Actually, I don't need that vector distinctly by itself because I'm, of course, going to just use these components A and B to build my general solution. But anyways, it's worth stating that we know that that's true. Now that I've got all of these ingredients, I can state my general solution. There is my general solution. I've gotten accustomed to putting a box around my general solutions, but I don't think I have a box big enough for that particular one. But that's okay. And now I was provided initial conditions in the statement of the problem, and so I'll need to plug in that initial condition to be able to solve for these constants. And at first glance, this function, these two functions, x1 and x2, that we've written in vector form here, just seem like a mess. And so it might be a little intimidating to have to try to think about incorporating initial conditions. But remember that my initial condition in this particular case is in terms of t equals 0, and most of the functions that are involved are very well behaved at t equals 0. So I think if I plug in t equals 0 on this right-hand side of my general solution, the expression that results will actually be pretty manageable. So let's give it a shot. And actually, in solving for these constants, C1 and C2, I have uncovered another typo in these notes. Again, I will post the corrected version. So if you're looking at the notes right now and they look different from the ones that I'm using here, then that's because I have corrected these typos and posted the corrected notes online. The issue here was in the form of the general solution that I wrote up earlier on this page, and I just had the sine and the cosine swapped here. So as I said, I'll fix that typo when I post the notes online. Based on this corrected version of the general solution, when I plug in my initial conditions and solve the resulting system for C1 and C2, it looks like I get C1 equals -2 and C2 equals -3. So I can write my actual solution. And this is the form of that solution when I just drop C1 and C2 into my general solution. But in this particular case, especially when we solve for when we incorporate initial conditions, it is kind of helpful to go ahead and write out the two distinct solutions, x1 and x2. As you can see, there will actually be some like terms. I'll have e to the negative 2t cos of t over here with some coefficient. I'll have a similar term over here. So it is helpful to go ahead and just collect those like terms. Let me show you what that looks like. So combining all of the components from the first row, I believe I get this function here for x1. And as I expected, there were like terms that I could simplify. So I simply have e to the negative 2t cos of t minus 5 sine of t. x2 is a very similar function, just slightly different coefficients. And these are, of course, the types of functions that we're very familiar with from chapter 3. These are overdamped oscillations because in theory, there's some oscillation caused by these trig functions, but the exponentials are so strong that they're driving the solutions to zero almost immediately. Just for reference, I've graphed them here. X1 passes through 1 at t equals 0 as determined by the initial condition, and then kind of has one sort of oscillation, and then effectively, if we were to zoom in, we might be able to see some more oscillation, but effectively just returns to equilibrium. And then similarly with x2, it does pass through negative 2 as predicted by our initial condition, and then more or less heads immediately to 0 because of the strength of this exponential driving it to 0. All right, let's take a look at one last example for this section. Okay, we'll start as usual by finding the eigenvectors. Actually, we'll start as usual by pointing out a typo. There should just be an x vector on this matrix here. I'm really on a roll with these notes. Apologize for that. But having recognized that, now we're going to call this our matrix A, and we'll find the eigenvectors and eigenvalues of this matrix. So this is a sort of interesting case because I have worked through the steps to find my eigenvalues, and I actually have one real eigenvalue and then two eigenvalues that are complex conjugates. I'll just point out quick that in working through the algebra, I got to a point where I just needed to use some resources. So I actually got the roots of this characteristic polynomial using an online resource. But anyways, one way or the other, I got my eigenvalues, and we know that if I have complex eigenvalues, they always come in a pair. So the fact that this was a 3 by 3 matrix indicates that I could get two complex eigenvalues as I have here, but then the third would have to be real because it would be impossible to have three complex eigenvalues because, again, complex eigenvalues always come in pairs. Now that I have identified these eigenvalues, I'll find the corresponding eigenvectors, and I'll just acknowledge ahead of time that it's going to be a little tricky plugging this in with the square root of 2 and the I, etc. And so I'll probably utilize some resources there as well, but let's go ahead and give it a shot. Let's start with lambda equals negative 2, find that eigenvector, and then select one of these complex eigenvalues and find its corresponding eigenvector. Here's the eigenvector associated with lambda equal to negative 2. Let's go ahead and work through the steps to find an eigenvector for one of these complex eigenvalues. As I predicted, this process of finding the eigenvector associated with lambda equal negative 1 minus root 2i is a bit of a mess. I've worked through the steps here for the most part. I started reducing this matrix, and then I just got to a point where the calculations were just getting pretty crazy. So I went ahead and used a computational resource to be able to identify my eigenvector. Problems that are this messy, I mean, we won't encounter them very often. And really the point of this problem is not necessarily to get bogged down in these algebraic details, but just to see how to combine solutions of different types into our general solution. So I believe I've got all of the necessary ingredients. I've got eigenvector associated with the one real eigenvalue. And then, as we've seen recently, once I've found one eigenvector associated with a complex value, I know that the other eigenvector associated with the other eigenvalue will simply be the conjugate. And as we've also seen, I don't build my solution out of those two separate eigenvectors, namely like eta 1 or eta 2. I instead use these two component ingredients within one of the eigenvectors. So, as I said, I believe I've got all of the details I need. So let's go ahead and take a deep breath and try to write out my general solution. Hopefully I've got enough room down here at the bottom of the page. And true to form for this lecture, I did have another typo. I just had this sign incorrect here. But with that small detail fixed, I believe I've written out my general solution. And as I mentioned, the key takeaway that I just want to point out is that we can combine different types of solutions into one general solution. So here we have kind of a standard, real, distinct eigenvalue of -2. So I just built a constant times a corresponding eigenvector and then e to the -2t. And then my other two eigenvalues were complex conjugates. And so I used them, according to the formula introduced in this section, to build these latter solutions. So in theory, we could have any sized matrix and get any combination of complex conjugate or real eigenvalues, and we could combine them as necessary to make one general solution. All right, that wraps up section 5.8. In the next section, we'll look at the third case regarding the different types of eigenvalues we could get. Specifically, we'll be looking at possibility of getting a real eigenvalue that is repeated, that has multiplicity 2. So that will be in the next section.